What if you could instantly spot the missing puzzle piece in a sequence, no matter how jumbled it gets? Missing number is a classic Pattern Mastery 100 question and an interview favorite for Google and Facebook. Many candidates overcomplicate it, but with the right insight, you can solve it in a single pass, using simple math or bitwise tricks. Mastering this problem proves you see the bigger pattern, not just the details. Let's break it down. You're given an array containing n distinct numbers taken from the range 0 to n. There's exactly one number missing. Your task is to return that missing number. Now let's assess the challenge. A brute force approach might use a set or check each number, but that's extra space or O(n) squared time. Can we do better? Yes, two clever ways. Math approach: the sum of numbers from 0 to n is n times n plus 1, divided by 2. Now subtract the sum of the array, and you get the missing number. Bitwise approach: XOR all numbers in the array, then XOR that with all numbers from 0 to n. Matching numbers cancel each other out. What's left is the missing number. Both ways are O(n) time and O(1) space, perfect for interviews. Let's structure the mathematical approach. Compute the expected sum from 0 to n. Compute the actual sum of the array. Subtract the actual sum from the expected sum to get the missing number. Or structure the XOR approach. Initialize missing to n. XOR all numbers in the array with all numbers from 0 to n. The result is the missing number. Let's try to implement it using solution 1. Here we're defining a function called missing number that takes an array named nums. This array is supposed to contain numbers from 0 to n, but one number is missing, and our job is to find that missing one. We store the length of the array in n. If the array has length n, that means it should have contained n plus 1 numbers total, from 0 to n, but 1 is missing, so only n are present. This calculates the sum of all numbers from 0 up to n using a shortcut formula. Instead of adding them one by one, we use n plus 1, 2. Think of it like calculating the total price of a full set of items without scanning each item individually. Now we create a variable called actual and set it to 0. This will store the sum of the numbers we actually have in the array. We loop through every index in the array, from 0 up to nums.length, 1. Time complexity note: this loop runs once per element, so this is where the O(n) comes from. Each time through the loop, we add the current number into actual. So by the end, actual becomes the total sum of all the numbers present in the array. This closes the loop, meaning we finish summing every number in nums. Now we subtract the sum we actually saw from the sum we expected to see. The difference is exactly the missing number, like noticing which amount is missing from the full total. And that's the end of the function. And that's how this algorithm works. It first computes the expected sum from 0 to n, then it sums what's actually in the array and subtracts to reveal the missing value. Efficient, simple, and elegant. Let's test our function using this input: 3, 0, 1. These numbers represent a list containing unique values from 0 up to n, with exactly one number missing. Here's why the solution works. We compute what the total should be for numbers 0 through n, then subtract what we actually have in the array. In this case, the array length is 3, so n equals 3. The expected sum of 0 plus 1 plus 2 plus 3 is 6. The actual sum of the array 3 plus 0 plus 1 is 4, so the missing number is 6 minus 4 equals 2. And that's exactly what our program outputs, 2. The code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the missing number by comparing the expected total with the actual array sum, efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called missing number that takes an array nums. This array contains numbers from 0 to n, but one number is missing, and our job is to find that missing one using XOR. Time complexity: O(n) because we scan through the range once and the array once. We store n as the length of the array. Since one number is missing, the full range should be 0 to n inclusive, that's n plus 1 total numbers, but we only have n numbers in the array. We create a variable called XOR starting at 0. This will act like a running XOR bucket where we combine values. First loop, we XOR together every number from 0 up to n. A quick XOR fact: if the same number appears twice in XOR, it cancels out and becomes 0, like pairing identical socks and removing the pair. So later, when we XOR the array numbers 2, all the matches will cancel. Second loop, now we XOR in every number that actually exists in the array. All the numbers that appear in both places, the full range and the array, will cancel each other out. The only thing left uncancelled is the number that never showed up in the array, the missing number. Now we return XOR, which at this point holds the missing value. And this last line closes the function. Done. And that's how this algorithm works. It first XORs all numbers from 0 through n, then XORs all numbers in the array to cancel matches, leaving only the missing number behind. Efficient, simple, and elegant. Let's test our function using this input. 0, 1. These numbers represent a list of unique values from 0 up to n, with one number missing from that full range. Here's why the solution works. We use XOR to cancel matching numbers out. When the same value appears twice in an XOR chain, it disappears, because a equals 0. So if we XOR all numbers from 0 to n, and then XOR all numbers in the array, everything cancels out except the missing number. For example, here n equals nums.length equals 2, so the full range should be 0, 1, 2. First we XOR the range, 0, 1, 2. Then we XOR the array, 0, 1, the 0 cancels with 0, the 1 cancels with 1, and the only thing left is 2. And that's exactly what our program outputs, 2. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the missing number by XOR, canceling the full range against the array values. Efficient, accurate, and reliable. Alright, let's wrap it up. This problem was all about finding one missing number in a sequence, a clean logic puzzle that tests how well you think mathematically and bitwise. Breakdown recap. We started with an array of unique numbers taken from 0 to n, but with one number missing. Our job was to figure out which one. Simple conceptually, but it's a great test of how you handle efficiency and space optimization. Assess recap. We explored different methods. The brute force approach, while straightforward, isn't efficient. Instead, we looked at two elegant ON solutions: the mathematical approach using the formula for the sum of the first n numbers, and the XOR trick where matching pairs cancel each other out, leaving the missing value behind. Both methods are smart, fast, and memory efficient. Structure recap. The logic came down to this: calculate the expected total or XOR pattern, then compare it to what we have in the array. The difference, or the leftover bit, is our missing number. Implement recap. We implemented both approaches on LeetCode, and the code ran smoothly without any errors. Check recap. After testing across various cases, the results were consistent, confirming that both methods worked perfectly and efficiently. The key takeaway? When facing a problem like this, look for mathematical patterns or bitwise symmetry. The simplest ideas often lead to the most optimal solutions.